All right, get ready for this one, folks, because today we're diving deep into probabilistic data structures.
Probabilistic data structures.
You've probably heard the name,
You've probably heard of them.
but you might not know what they are or why they're so cool.
Yeah, these things are quietly powering so many apps that we use every day. It's kind of crazy.
Right, like how does Google Chrome instantly know when to block a bad website? Or how does Medium recommend articles that seem to be exactly what you're interested in?
Chances are a probabilistic data structure is doing all that work behind the scenes, making those decisions in like a split second.
So today we're going to unpack all of that. We've got a ton of research here about how these things actually work.
Yeah, let's get into it.
So let's start with bloom filters. I feel like everyone's heard of bloom filters.
Say bloom filters.
What are they really?
Well, they're all about speed. So like a bloom filter can quickly figure out if something's probably in a set.
Probably.
Probably.
No, definitely.
Yeah, and it does all this with like a super simple setup.
What do you mean?
I mean, just a bit array and some hash functions.
So basically, you're using those hash functions to create a unique fingerprint for each item that you want to add to the set.
Exactly. And then by checking those fingerprints, the Bloom filter can tell you with pretty high certainty whether or not you've seen that item before.
Okay, that makes sense. So that's perfect for something like Chrome blocking bad websites, right?
Right.
Because they can store like a huge list of malicious URLs in a Bloom filter and then check new websites against it almost instantly.
Yeah. And even if there's like a rare false positive.
Which could happen, I guess.
Right. But even if there is, the delay is tiny compared to the protection it offers.
So it's worth it.
Totally.
But it's not just security. Our research also said that Medium uses Bloom filters for recommending articles.
They do.
So I'm guessing that helps them figure out which articles a user has probably already seen.
Yeah, exactly.
Yeah.
So by figuring out those connections between articles and users, Bloom filters can like personalize those recommendations without having to store every single article a user has ever read.
That makes sense because that would be a ton of data.
Way too much.
And I'm also seeing here that Cassandra, which is like a database, uses Bloom filters to make queries way faster.
Yeah, because it's all about minimizing those unnecessary lookups.
Yeah.
So before diving into a database, a Bloom filter can just do a quick check to see if the data is even there.
Okay, so Bloom filters are great for checking set membership, but what about if you want to know how often something appears, like how many times something has shown up in a data set?
Ah, you're talking about Count Min Sketch.
Count min sketch.
Yeah, so think of Count Min Sketch like it's the tool for finding the popular kids in your data, like the elements that show up most frequently.
Okay, and so instead of a bit array, this one uses like a matrix of counters, right?
Yep, still using hash functions though.
So how does that work?
Well, to figure out how often something appears, you actually look for the smallest count among all the counters that it's mapped to.
The smallest, why not just like add them all up? Wouldn't that be more accurate?
Yeah. You'd think so, right? But you have to account for collisions because, like, multiple elements could end up being mapped to the same counter. So taking the minimum makes sure that you never overestimate the true frequency.
Okay, so it's like being a little bit conservative.
Yeah, just to be safe.
So where would you actually use this count min sketch in the real world?
Oh, tons of places. So,
Right.
like, imagine trying to find suspicious activity on a network like a Countman sketch could help you track IP addresses and really quickly figure out which ones are sending or receiving a ton of traffic, which could be a sign of a problem.
So it's like figuring out which IP addresses are suddenly the life of the party sending way more data than usual.
Yeah, exactly.
And that same idea could apply to databases too, right?
Right, like for database query optimization. So by estimating how big the results will be during a query databases, can make smarter choices about how to process the data, which just makes everything run faster.
Okay, that's starting to make sense to me. I'm seeing how these probabilistic data structures can be applied to so many different problems. And speaking of applications, I'm thinking about how CountMin Sketch helps find frequent items. It makes me think about natural language processing, like, sifting through a ton of text to find the words that are used the most often.
Totally. In natural language processing, we always need to figure out word frequencies in these huge data sets. And Countman Sketch is great for that. It lets us efficiently estimate those frequencies without having to store every single word in its count.
Okay, so instead of having a giant dictionary, we get like a compact sketch that gives us a decent idea of what words are showing up the most.
Yeah, exactly. And this info is super important for things like building language models, or figuring out the main themes in a piece of text, or even detecting spam.
So many applications.
It's amazing, really.
Okay, so we've talked about checking for membership with Bloom filters and finding those frequent items with Countman Sketch. But what about if you want to figure out how many unique items are in a set?
You're talking about hyperlog log.
Hyperlog log, that one sounds complicated.
It does, but it's super useful because it lets you estimate how many unique elements are in a set, even if the data set is absolutely massive. And the best part is it does all this without actually storing all of the elements.
Wait, how is that even possible?
Well, it uses this clever combo of hash functions and a bit of probability theory.
Probability theory.
Yeah, so it looks for patterns in the binary representation of the hashed values to estimate the number of unique elements.
Binary representation, so like ones and zeros again?
Yep, it analyzes the longest run of leading zeros in the binary form of the hashed values. The rarer those long runs are, the more unique elements there must be.
So it's kind of like flipping a coin and getting heads like 10 times in a row. The more heads you get, the less likely it seems, so you start to think something's up.
Exactly. And hyperlog log basically applies that same principle to hash values, so it can accurately estimate the number of unique elements even in massive data sets,
Yeah.
all while using very little memory.
That's pretty clever. Can you give me an example that I might actually encounter in the real world?
Sure, imagine you're running a really popular website and you want to track the number of unique visitors you have each day using hyperlog log. You can do that even with millions of visits without storing every single IP address.
I see. And our notes say that Redis, another database, uses hyperlog log to offer a command called pfcont, which does exactly that. It estimates the number of unique items in a set.
Right, and Google Analytics relies on hyperlog log too to track unique visitors across all sorts of websites.
So it's kind of the unsung hero of web analytics.
For sure, and its applications go way beyond just web analytics. Like, it's also used in data warehousing for doing distinct count analyses on huge data sets, which helps analysts identify important trends and patterns.
So hyperlog log is pretty important.
Very important.
Okay, so we've got Bloom filters for checking membership Countman Sketch for figuring out how often things appear, and hyperlog log for counting those unique items.
Those are the big three.
But I'm guessing there's even more.
Of course.
What else is there?
Well, let's move on to the cuckoo filter. It's kind of like a cousin of the Bloom filter, but with a cool advantage.
Oh yeah, the cuckoo filter, I remember from our notes that it can handle deletions?
Yeah, which Bloom filters can't really do easily.
Right, so how does the cuckoo filter pull that off?
Well, it uses a hash table with two hash functions. So each element gets mapped to two possible spots in the table. And if both of those spots are full, the algorithm will kick out one of the existing elements to make room for the new one. And that's why it's called the cuckoo filter.
So it's kind of like musical chairs, but with data.
Uh-huh. That's a great way to think about it.
Yeah.
And this kicking out process can create a chain reaction, but the structure is designed to minimize those collisions.
Okay, so it sounds kind of chaotic,
It does a little.
but I guess it works out in the end.
It does. That's the amazing thing about the cuckoo filter. It manages all this chaos and still allows both insertions and deletions while keeping storage super efficient.
So where would you use something like this?
Well, one example is in network routing. Think about how much info routers need to store to direct all that internet traffic. Cuckoo filters provide a really compact way to store that routing info so routers can find paths quickly without using a ton of memory.
So another example of striking that balance between efficiency and being able to work at a massive scale.
Exactly. And they're not just for network routing either. They're also used in distributed databases to manage data consistency and efficiently track which nodes hold which data.
And I see that content delivery networks, or CDNs, also use cuckoo filters.
Yeah, because CDNs are all about storing content closer to users to speed up website loading times. And cuckoo filters help them track what content is stored where, ensuring that users can get what they need super quickly.
So whether it's routing data or managing massive databases or delivering content to our devices, cuckoo filters are working behind the scenes, making everything smoother and faster.
Totally. They're like the unsung heroes of the internet.
Okay, so we've got Bloom filters for checking membership Countman Sketch, for how often things appear, hyperlog log for counting unique items, and cuckoo filters for adding that dilution functionality. But there's still one more, right?
Yeah, there's one more. It's called locality sensitive hashing, or LSH.
LSH, this one sounds kind of mysterious. What is that one all about?
It's all about finding similar items even when we're dealing with data that's hard to visualize.
What do you mean by hard to visualize?
Like, imagine you're trying to find similar images in a database of millions of pictures, comparing every pixel would take forever.
Right.
LSH provides a shortcut by finding images that are likely to be similar without doing all those comparisons.
So instead of getting bogged down in the details, it's looking for like those big picture patterns that suggest similarity.
Exactly. It uses a bunch of hash functions that are sensitive to distance. So items that are close to each other in the original data space are more likely to end up in the same bucket when you use these special hash functions.
It's like sorting items into bins based on how much they look alike, right? Things that share a lot of features end up in the same bin.
Yeah, that's a good analogy. And
Yeah.
the key is that this binning process is way faster than comparing every single item to every other item.
So it's like another shortcut.
Another shortcut.
I'm starting to see a pattern here.
Uh-huh.
Okay, so that's the theory, but how is this LSH actually used? What are some real-world examples?
One really common use is an image search. So when you upload a picture to Google Image Search, LSH is what helps them find similar images from their giant database.
So when I upload a picture of my dog and it shows me other pictures of dogs, even if they're not the exact same breed, that's LSH in action.
Exactly, and it's not just about finding exact copies either. LSH can find images that share similar features like colors or shapes or textures.
That's really cool, and it seems like LSH would be useful in recommendation systems too, right? The systems that suggest movies or products or music based on what you've liked before.
Yeah, for sure, because recommendation systems are all about finding users with similar tastes, and LSH can help group users together who have liked similar things. So the system can then recommend things that others in that group have enjoyed.
So it's not just about comparing items, it's also about finding patterns in people's preferences and behaviors.
Exactly. And here's another cool application, document deduplication. So imagine you have a ton of documents and you need to find near identical copies to get rid of duplicates. LSH can help find those documents that are almost the same, even if there are some minor differences in the words or formatting.
So it's like having a super-powered plagiarism detector.
Pretty much. And that's just the tip of the iceberg.
Yeah.
LSH can be used for so many things, like in bioinformatics for comparing DNA sequences or protein structures.
Wow, so LSH really is like a universal similarity finder working across all sorts of data to uncover those hidden connections.
It's amazing what it can do.
Okay, we have covered a lot today. Bloom filters, Countman sketches, hyperlog cuckoo filters, and LSH. It's incredible to see how these concepts that seem kind of complicated at first have such a huge impact on the applications we use every day.
It really is. It speaks to how creative computer scientists and mathematicians are constantly pushing the boundaries of what we can do with data.
I'm feeling a bit overwhelmed, but in a good way, it's like my brain is expanding to fit all this new information.
I know the feeling.
Okay, so before we move on, let's just take a step back and summarize what we've learned about probabilistic data structures. They might seem complex, but they're really all about finding clever ways to handle massive data sets efficiently.
Exactly. It's about finding that sweet spot between accuracy and efficiency, because in a lot of cases, a little bit of approximation is a small price to pay for the huge gains in speed and storage that these structures offer.
And they're not just theoretical either. They're powering some of the most widely used applications out there, like blocking malicious websites, recommending new music, all sorts of things.
And as data keeps growing exponentially, these structures are just going to become more important. They're essential tools for anyone who's working with big data.
So if someone's listening to this and they're thinking, why should I care about this? The answer is because these probabilistic data structures are shaping the future of how we interact with information.
That's a great way to put it. And the more we understand how they work, the better equipped we'll be to navigate this data-driven world.
Now, before we move on, something's been on my mind since we started talking about these structures. They all seem to rely on this concept of randomness. We've talked about hash functions and probability, but I'm still a bit fuzzy on how randomness actually helps make these structures work so well. Can you shed some light on that?
Absolutely. That's a great question, and it gets to the heart of what makes probabilistic data structures so unique. To really understand why randomness is so important, we need to think about the challenges of working with truly massive data sets.
When you say massive, how big are we talking?
I mean, data sets that are so large that they can't be stored or processed using traditional methods. We're talking billions of data points, terabytes of information, the kind of data generated by social media platforms, sensor networks, scientific experiment.
Okay, so we're dealing with data that's just too big to handle in a conventional way. How does randomness help us overcome that obstacle?
We'll think about it this way. Randomness lets us sample the data cleverly without having to look at every single data point.
Sample, like taking a small representative portion of the data.
Exactly. But instead of taking a random sample in the traditional sense, probabilistic data structures use hash functions to create a fingerprint for each data point.
Those hash functions we talked about earlier, the ones that take any input and produce a unique code.
You got it. And the randomness comes in because these hash functions distribute those data points across the structure in a way that's statistically predictable, but also kind of random.
Okay, so instead of storing every single data point, we can store these fingerprints and use them to make inferences about the data as a whole.
That's the key. And because those fingerprints are so much smaller than the original data points, we can store way more info in a much smaller space.
That's where the efficiency comes in. We're essentially trading a bit of accuracy for huge gains in storage and speed.
Precisely. And the brilliance of probabilistic data structures is that they're designed to minimize the impact of that trade-off. The randomness is carefully controlled to ensure that the results are still statistically reliable.
So it's not just blind luck. There's a lot of clever math and statistical analysis going on behind the scenes to make sure these structures actually work.
Absolutely. Randomness is a tool, not a gamble.
Uh-huh.
It's used strategically to overcome the limitations of traditional data structures. And it allows us to analyze massive data sets in ways that just weren't possible before.
That's amazing. It's like we're learning a new language, the language of data at scale.
That's a great analogy. And speaking of language, we briefly mentioned how these structures are used in natural language processing, or NLP, and I'd love to dive deeper into that world and explore how probabilistic data structures are helping us understand the vast universe of text data.
I'm totally with you on that. NLP has always fascinated me. It's like we're teaching computers to read between the lines to understand the nuances of human communication.
Exactly. And as we delve deeper into NLP, we'll see how those probabilistic data structures play a crucial role in uncovering hidden patterns and extracting meaning from all the words that surround us. But for now, let's take a short pause to gather our thoughts and get ready for the next part of our journey.
Sounds good. I need a coffee refill.
Me too.
So before we took a break, we were talking about how randomness plays this crucial role in making these probabilistic data structures so efficient.
It's like we're cracking the code of big data.
Exactly. And speaking of cracking codes, you mentioned how these structures are used in natural language processing, or NLP. I'd love to hear more about that.
NLP, it's all about teaching computers to understand the nuances of human language. But one of the biggest challenges is dealing with the sheer volume of text data that's out there.
Yeah, we're talking about everything from books and articles to social media posts and online reviews. It's like an endless sea of words.
Exactly. And within all those words, there are hidden patterns and relationships waiting to be discovered. That's where probabilistic data structures can really help.
Okay, so how do these structures help us make sense of all that text? Give me a specific example.
Let's take topic modeling, for instance. Imagine you have this huge collection of news articles, and you want to automatically group them into different topics, like politics, sports, entertainment.
That sounds like a really tough task, even for a human.
It is, and that's where a probabilistic data structure called latent Dirichlet allocation, or LDA, comes in.
Oh.
LDA uses a statistical model to identify those underlying topics that are present in a collection of documents.
LDA, that rings a bell. Isn't that related to those topic clusters you see in search results sometimes?
You got it. A lot of search engines use LDA or similar techniques to group those search results into meaningful categories.
So instead of just matching keywords, LDA is trying to understand the underlying themes and concepts that connect those documents.
Exactly. And the really cool thing about LDA is that it's probabilistic. It's not trying to find a perfect one-to-one mapping between a document and a topic.
So it recognizes that some documents might touch on multiple topics, or that there might be some overlap between categories.
Precisely. LDA allows for ambiguity, which makes it much more robust when dealing with real-world text data, because real-world text is messy and complex.
That makes sense. It's more flexible.
Yeah, much more.
Okay, I get the big picture, but how does LDA actually work under the hood? Does it involve those hash functions and bit arrays we talked about earlier?
It's a bit more complex than that. LDA relies on a statistical model that assumes each document is a mixture of different topics, and each topic is a distribution of different words.
So like each article is a blend of different themes, and each theme is characterized by a certain set of words.
Exactly. And LDA uses an algorithm to estimate those distributions of topics and words.
It figures it out.
It figures it out. It's like an iterative process where the algorithm starts with an initial guess and then keeps refining it based on the words it actually sees in the documents.
So it's like constantly learning and adjusting its understanding of the topics and the words to better fit the data.
Exactly, and that iterative process combined with the probabilistic nature of the model makes LDA really good at discovering those hidden topics, even when dealing with huge, noisy data sets.
It's incredible how these probabilistic techniques can reveal patterns in language that we might not even consciously notice as humans.
That's what makes NLP so fascinating, the ability to use computational methods to gain a deeper understanding of how we communicate.
It's like we're giving computers the sixth sense to perceive meaning and context beyond just the words themselves.
It's a powerful analogy, and it really highlights the potential of NLP to completely change how we interact with information.
I mean, it's already happening. Think about chatbots, machine translation, personalized news feeds. All of these applications are powered by NLP, and probabilistic data structures are playing a key role behind the scenes.
For sure. And as the field of NLP keeps evolving, we're going to see even more innovative applications that use these probabilistic data structures to process and understand human language in ways we haven't even imagined yet.
I can't wait to see what they come up with.
It's an exciting time for sure.
Okay, so before we get too carried away with the future of NLP, let's bring it back down to earth for a bit. Our research mentions some really interesting applications of probabilistic data structures in databases. Can you tell me more about that?
Absolutely. Databases are essential for so many modern applications, from e-commerce websites to social media platforms. And as these applications grow bigger and more complex, databases have to deal with this ever-increasing amount of data.
It's like they're the librarians of the digital world, trying to keep everything organized and accessible in this vast and ever-growing library.
That's a perfect analogy. And just like librarians need efficient tools to manage their massive collections, databases rely on sophisticated techniques to handle the information they store.
And that's where probabilistic data structures come in to the rescue.
That's exactly what they do. They provide this powerful set of techniques for optimizing database operations, making them faster, more efficient, and more scalable.
Okay, give me a real-world example of how these structures are being used in databases today.
Let's talk about query optimization. Imagine you're searching for a product on an e-commerce website behind the scenes. The website's database is executing a query to find all the matching products.
Right.
And probabilistic data structures can help the database estimate the size of the intermediate results during the query execution.
Intermediate results, what does that mean?
Think of a complex query as a series of steps. Each step produces a subset of data that's then used in the next step. And probabilistic data structures like Count, Sketch can be used to quickly estimate how many records will be returned at each step without having to process all of the data.
So it's like taking shortcuts, figuring out which paths are most likely to lead to the desired result without having to explore every single option.
You got it. And this information helps the database choose the most efficient way to execute the query, minimizing the amount of data it has to process and speeding up the overall query time.
So it's all about making smarter decisions about how to navigate the data using probabilistic estimates instead of doing those exhaustive calculations.
Precisely. And this can lead to some pretty significant performance improvements, especially when dealing with those large and complex queries.
This is fascinating. Our research also mentioned something called Bloom joins. What are those and how are they related to Bloom filters?
Bloom joins are a clever technique for optimizing a specific type of database operation called a join. A join combines data from two or more tables based on a shared key.
So if you have a table of customers and a table of orders, you could use a join to find all the orders placed by a particular customer.
Exactly. And Bloom joins use Bloom filters to make this process faster. Remember, Bloom filters are really good at quickly checking if an element is likely to be in a set.
Right.
So let's stick with our customer. An order example before performing the join. You could create a Bloom filter for each table containing the keys that are present in that table.
So the customer Bloom filter would have all the customer IDs, and the order Bloom filter would have all the order IDs.
You got it. And then as you go through each row in the customer table, you can use the order Bloom filter to quickly check if there are any matching orders for that customer.
And if the Bloom filter says no, you can skip that customer and move on to the next one without even looking at the order table.
That's right. And if the Bloom filter says yes, then you go ahead and do the actual join operation. This approach can significantly reduce the amount of data that needs to be processed, especially when one table is way bigger than the other.
So it's like using the Bloom filter as a preliminary screening step to filter out the unlikely matches before you do the heavy lifting of the join operation.
Exactly. And this can lead to huge performance gains, especially in those large-scale database systems.
It's incredible how these probabilistic data structures are finding their way into every corner of data processing, from search engines and NLP to databases and network routing. They're
They
everywhere.
really are, and their applications just keep expanding. They're being used in all sorts of fields like bioinformatics, computer security, machine learning, and beyond.
Okay, I'm ready to be blown away. Tell me more about how these structures are being used in those cutting edge areas.
Well, in bioinformatics, for example, probabilistic data structures are being used to analyze those massive genomic data sets. Imagine you're trying to compare the DNA sequences of two different species. This involves analyzing billions of base pairs, which is incredibly computationally intensive.
I can imagine.
And probabilistic data structures like Bloom filters and Countman sketches can help speed up this process by efficiently identifying regions of similarity and difference between those sequences.
So instead of comparing every single base pair, we can use these structures to zero in on the areas that are most likely to be interesting or informative.
That's the idea. And this can significantly speed up genomic research, helping scientists discover new insights about how living things work and how they evolved.
That's amazing. You also mentioned computer security. How are these structures being used to protect our data?
One important application is in intrusion detection systems. These systems constantly monitor network traffic for suspicious activity, like someone trying to hack into a server or spread malware, and probabilistic data structures can help these systems efficiently track patterns of network activity and quickly identify anything unusual that might indicate a security breach.
So it's like having this watchful guardian constantly scanning the network for signs of trouble, using these probabilistic techniques to sift through massive amounts of data and find those potential threats.
Exactly. And by using probabilistic data structures, these security systems can operate at a huge scale, handling all the data that flows through modern networks without slowing down or sacrificing accuracy.
It's like having a superpower.
It is.
What about machine learning? I've heard that probabilistic data structures are playing a role in developing artificial intelligence.
That's right. Machine learning algorithms often rely on massive data sets to train models that can make predictions or decisions, and probabilistic data structures can help make that training process faster and more efficient.
So even in the realm of AI, we're seeing this trend of using randomness and approximation to handle those massive data sets and speed up those complex computations.
It's a powerful approach, and it shows how versatile and powerful these probabilistic data structures are. They're becoming essential tools for anyone working with big data, no matter what field they're in.
This is really remarkable. It seems like probabilistic data structures are quietly shaping the future of technology, driving innovation in so many different areas of our lives.
It's a really exciting time to be working in this field, and the best part is we're only just starting to explore the full potential of these structures.
I can't wait to see what the future holds.
Me neither.
Okay. I'm feeling a bit overwhelmed by all the amazing information we've covered today, but in a good way. It's like my brain has been stretched and expanded to make room for all these new concepts.
I know the feeling is the thrill of discovery.
But before we get carried away with all the possibilities, let's take a short break to let everything sink in. When we come back, we'll explore what the future holds for probabilistic data structures and what this all means for our data-driven world. Wow, what a journey through the world of probabilistic data structures. It's amazing how these seemingly complex concepts are actually powering so many of the technologies we use every single day.
It really is. We've covered Bloom filters, Countman sketches, hyperloglog, cuckoo filters, locality-sensitive hashing.
The list goes on, and what strikes me is how they've really changed the way we think about accuracy in computing.
Yeah, it's a different mindset.
We're so used to the idea that computers should always give us these perfectly precise answers, like ones and zeros, black and white,
But probabilistic data structures show us that there's another way.
instead of always striving for that perfect accuracy, which can be really computationally expensive, especially when you're dealing with massive amounts of data.
Right. Sometimes it's just not feasible.
We're learning to embrace this idea of approximation as a powerful tool.
And what's remarkable is that these structures are designed to minimize the impact of that trade-off.
Right.
It's not just about throwing accuracy out the window.
Exactly. The randomness that's introduced is very carefully controlled to make sure that the results are still statistically reliable, still meaningful.
It's about finding that sweet spot between precision and practicality.
Right, because in so many real-world applications, a probabilistic answer is more than enough, especially when you consider the massive gains you get in terms of speed and storage and scalability.
Yeah, it's like choosing the right tool for the job. Sometimes you need a scalpel. Sometimes a hammer is just fine.
So, in a sense, we're kind of learning to be comfortable with a little bit of uncertainty in our quest to understand data.
Uncertainty is part of the equation, especially when you're dealing with massive data sets.
Yeah, and I think that's a really valuable skill to have, especially in today's data-driven world. Being able to handle that ambiguity, being okay with a bit of approximation, I think that's only going to become more and more important as we move forward.
Absolutely. It allows us to unlock insights that would otherwise be hidden or just too computationally expensive to uncover.
So, as we wrap up this incredible deep dive, I'm curious to get your take on the future of probabilistic data structures. Where do you see this field heading in the years to come?
Well, I think we're just scratching the surface. As the volume of data continues to grow at this incredible pace, probabilistic data structures are going to become even more essential.
Right, we need these tools to make sense of it all.
Exactly. I think we can expect to see even more creative and sophisticated structures emerge, pushing the boundaries of what's possible with data processing.
And what about new applications? Where do you see these structures being applied in the future?
Oh, the possibilities are endless. We might see them used to personalize medical treatments,
Hmm.
optimize energy grids, maybe even predict and mitigate the effects of climate change.
Wow, that's incredible. It's inspiring to think about the positive impact they could have on the world.
It really is. And the best part is, we're just getting started. There's so much more to discover and explore.
This has been such a fascinating journey. I feel like I've gained a whole new understanding of the world of data and the amazing algorithms that are helping us make sense of it all.
It's been a pleasure sharing this exploration with you. I hope it sparked your curiosity and encouraged you to keep learning.
It definitely has. And for our listeners who want to dive deeper, we'll be sure to include some resources in the show notes.
Remember, the world of data is vast and constantly evolving, so keep exploring, keep learning, and never stop asking those thought-provoking questions.
That's great advice. Thank you so much for joining us today for this deep dive into probabilistic data structures. Until next time, keep exploring the fascinating world of data.